Yeah, so let's talk about nitration. So nitration, again, is quite easy. So the only thing you need to take note of is you need to be able to draw the correct structures. If you draw the wrong structures, you mess up. So you start with your benzene. You react nitric acid in the presence of sulfuric acid. Sulfuric acid will act as your Lewis catalyst base, as your Lewis base catalyst. And then you produce some nitrobenzene, some water, and some sulfuric acid, similar to sulfonation, right? So the first thing you need to do is you need to be able to draw the correct structure of nitric acid. So nitric acid looks like this. So step 1 is electrophile generation, right? You need to generate your electrophile. So how do you go about generating your electrophile? It's quite easy. First thing, you get your nitric acid. So there is your nitric acid, looks something like this. Lone pair, double bonded, single bonded. This is supposed to be bonded to two things. It's bonded to one thing, so therefore it must carry a what? A negative charge. This is supposed to be bonded to 3, it's bonded to 4, and so it carries a positive charge. If that does not make sense, check out the other videos on halogenation and sulfonation. I explained this. And so this will react with some sulfuric acid. Sulfuric acid looks like this, like that. Lone pair, like that, right? First step, deprotonation. So this will be deprotonated. How will that look like? It will look like this. Which side should the arrow go? From electron rich to electron poor. So it will look like that. And then what will be the result? How will this look like? So we'll have the same part there, right? And then this part will be connected to this, like that, and then we'll deprotonate. So this proton is now here, like that. And then we're adding this to what? To this. To this. Take note, this is negative for the same reasons we've been discussing this entire time. Right? So at that step, what's the charge here? This charge, the formal charge on that oxygen is positive. Why? Because it's bonded to 4 things now. Now this is not happy being positive, and then to make matters worse, this is also positive, and so these two can repel each other, and then when they do that, this bond has to break, because this system here is not entropically favorable, right? So this will break. When that happens, what will you form? So you form something that will look like this. You have your, this will come down, so it will look something like that. Carrying a formal positive charge, and then you also have some water that will be evolved, right? And then you have your conjugate base. You have your conjugate base like that. So looking at this, step 1 is complete. This is our electrophile. This could participate as our base. This could participate as our conjugate base. So the reason I'm just calling this one a base is because water can either participate as an acid or as a base, right? But then this one has lost a proton, so therefore it is a conjugate base. So what's the next step? Attack. So we need to use this to attack a benzene. So I'll show that to you. Second step attack, right? So let me show you how that will happen. So you start off with your benzene like that, and then what do? You're using your electrophile. What do you expect to produce? So this electrophile could attack this bond here, and then when it does that, it could either move here or move here. So I'll decide to put it on the top there, so it will look something like this. This bond will break, and then there you have it. Right, and then one thing you'll be able to see is that you have your hydrogen there. Your hydrogen has not gone anywhere, and then this part here is electron deficient. Next step, resonance. In resonance, this is trying to gain stability, so we start with the same exact structure, which looks like this. So for simplicity, I'll just say NO2, so I don't have to draw too much. Like that. So first step, the formal charge is here. I mean the positive charge, or the carbocation is here. So if the carbocation is here, you know it will move here, right? It will come here. So it always skips a corner. The first thing, this comes here. There it is. This remains where it was, right? Second thing, this comes there. Here it is. This remains where it is. And then formal charge is there. So where did it move from? It moved all the way from here to there. And so this is your uranium ion. That is your uranium ion. So after doing that, the last step is restoration. Restoration of what? Restoration of aromaticity, right? So you need to restore your aromaticity, because this part has lost aromaticity because it's no longer planar. It's now sp3 hybridized, and so it's tetrahedral. So how do you restore aromaticity? You start with that same structure. So there it is. For simplicity, I'll just say NO2, but in an exam, please draw the full structure. Like that, right? Here's our positive charge there. And so, to restore aromaticity, what do we use? We always use the conjugate base. How did our conjugate base look like? It looked like this. So the more you practice, the easier it will be. Right? And so what happens? Deprotonation happens. And so it will happen in such a way that this proton will be deprotonated from there. And then the arrow should always go from electron rich to electron poor. So it should go this way. And then at the end of the day, what do you form when that happens? So you form nitrobenzene. You form nitrobenzene, right? But then it's in such a way that this pair of electrons will be used to reform the bond there. And then the bond has been reformed. What else will you form? We also had some water at some point, right? If you are following, you'll be able to remember where we had water. And then, because we've protonated this, it becomes sulfuric acid. And we've come back to our original equation. Sulfuric acid, water, nitrobenzene. That's how nitration is done. So if you liked the video, or if you'd like any improvements to be done, please comment. So that's the end of the video.